All right, so today we'll finish up section 1.3, and then we'll also take a look at 1.4. So the first function we're going to look at is called the greatest integer function. And can somebody just remind me from last time what a function is? Anybody remember? Or what test does a graph have to pass to be a function? Yep, Jane? It has to pass the vertical line test, which means that if you draw a vertical line, it never hits the graph more than once. Okay? Or if you want to say it a little more algebraically, it means that every input has exactly how many outputs? One. Every input has one output. So this function I'm about to show you fits the criteria we just said. And the greatest integer function is defined to be the biggest integer that's less than or equal to x. Okay, it's the biggest integer that's less than or equal to a specific integer that you're thinking of. And the symbol for it, there's a couple ways you can write it. We're going to see it written on the right-hand side with int on the calculator. You can also write it with kind of these like double, like it's like a bracket with an extra line in it. I think that's the symbol you'll see in the book. So if I said to you 5, if you took the number 5 and plugged it into the greatest integer function, what would you get as an answer? Well, Sam? Yes, you would get 5, because 5 is the biggest integer that's less than or equal to the integer that I said, 5. What if you plugged in, Caleb, what if you plugged in 4.9?
4.
You would get 4. Okay, because 4 is the biggest integer that's less than or equal to the number that I said, to x, 4.9. How about negative 2? What would you get if you plugged in negative 2? About Dylan?
Would you still get negative 2?
You would still get negative 2. How about if you plugged in negative 2.1? What's the biggest integer that's less than negative 2.1? Leo? Negative 2. How about negative 2.9? Still negative 2. All right, so it's like all of a sudden, and then you get to negative 3, and then it jumps up to negative 3 is the answer. So when you use the greatest integer function, what kind of numbers do you never get as an answer? Yeah? You never get decimals. Okay? You never get decimals. So let's take a look at what it looks like. Okay, so if we plug in, or you go to your y equals, do that first. You can clear anything that's in there from before. And I'm going to type math. And it's under number. Yeah. And it's the fifth option down. Int. Okay, and I have to put a variable in, so I'm just going to put in x and then close the parenthesis. Okay, and what I'm going to do is hit zoom 6. And you should get a graph that looks something like that. Okay, it almost looks like a set of stairs or like a set of steps. And to be a little bit more accurate than what the screen did, it should technically look like that. You want to kind of think of like as an open circle, closed circle on each end. Because when you're at 1, okay, down in this section, you don't include 1 in the section I just circled. That's why I put an open circle on it. It jumps up to 1. Okay? And then no matter what x value you pick between 1, including 1, up to 2, not including 2, the answer is always 1. Can anybody think of a situation in real life where this might model that situation? Where no matter what value you have, it's the same until you get to the next integer higher, and then it jumps up. How about maybe something with post office? Were you going to say something else?
Well, I was going to say, like, sometimes in word problems, if you just say how many tickets could you buy with $30, you can't buy like 4.5 tickets.
Okay, so you have to keep in mind rounding there. There's no no half ticket type thing. Yep. How about, anyone think of anything with the example that I just mentioned, like the post office, how that might apply? About mailing packages. How does that work when you mail a package? If you sell something on eBay, or does anybody do that? No? Does anybody know how it works? Yeah, no. So when you mail a package, you pay by the pounds usually. If it's under a pound, you pay by the ounce, or you can. But if it's over a pound, anything between 1 pound and 2 pounds costs the same amount to mail. Right? When you hit 3 pounds, then the price jumps up to the next price bracket. So anything between 3 pounds and then 3 pounds 15 ounces, you pay the same. When you hit 1 more ounce, it jumps up to 4 pounds, you pay the next price. So that's an example of where you could see something like that in that price structure of how the post office when you mail packages. Okay, so that's the integer function. Okay, it's also known as a step function because it kind of looks like a series of steps. All right, so I want to find a complete graph, which means, what's a complete graph again? What does that mean to do? How about, Tanya, do you remember what it means to find a complete graph?
When you can see like all of it.
Yeah, where you can see all the important points. If there's like turns in the graph or anything like that, you can see everything that's important in the graph. So they want us to find a complete graph of the integer function and then determine the domain and range. All right. So is the picture that I have on the graphing calculator, would you say that's a complete graph? Yeah. Yeah, there's nothing else that's going to happen. It's just going to keep being more of the same if you zoom out, or it's just those series of steps. So for a complete graph, I would use those x-mins, y-mins, and all that stuff. And that one was a -10. Okay, so again, for your window, you just have to write down those two and those two. Okay, now the domain. What numbers are you allowed to plug into the greatest integer function? Leah? Yeah, all real numbers. So our domain is from -infinity to +infinity. You can plug in anything you want. And now, what kind of answers do you get? What's the range here? Yeah? So we're on the right track. I think we can expand it a little more than whole numbers. Yep. Any integer. Why integers versus whole numbers? What's the difference? Yeah? Integers can be negative. So as far as the y values you get in this graph, it would be any integer. And the way you could write that is you could use the symbol for integers, which is a z, or you could just write it out, all integers. Okay, so there's your domain and range. All right, let's try another one, finding domain and range, because that usually seems to be a topic that sometimes people have trouble with. Okay, so we can get rid of the step function, so we're done with that for now. And I'm going to type in 16x minus x cubed. Now, I mentioned something about the highest exponent last week, and the number of turns that the graph can take. Does anybody remember what the connection was between the highest exponent and how many times the graph can turn on the screen? Jay?
Isn't it like one less?
It's one less. So this graph can turn up to, it doesn't have to, but it could turn up to 2 times. Okay, so let's graph it, and knowing that, we should be looking for those 2 turns. And if we don't see them on the screen, we have to adjust it. Okay, is that a good window? What do you think? How about Rebecca? No, it's not a good window because we don't see the turns. I can see it's going up and down, but I can't see where it kind of maxes out for that turn. All right, so doing that, what would I have to adjust here to make it so I can see those turns? Yep, I got to adjust both the y, the mins and the maxes. I'm just going to guess, and let's try 35. And for y min, let's try negative 35. And if that's not good enough, I'll come back and I messed it up. I'll do it again. So the x value, I accidentally adjusted that. I didn't need to. The y min, though, I adjusted. That one looks fine. And yeah, that's good. I would say that's a complete graph. Okay, because once we learn a little bit more about graphs of polynomials, we're going to learn that this section is just going to keep going down forever. This section is just going to keep going up forever. And there's the important part. You can see all the turns in the middle. Okay, so complete graph on this one. I would say that is a good window. Okay, so again, just those 2 and those 2. Any questions on that? Okay, domain and range. What values are you allowed to plug in for x in that formula? And if you're not sure, ask yourself, what values are you allowed to multiply by 16? And then what values are you allowed to raise to the 3rd power? And ask yourself, is there anything you can't do? Any of those operations I just said? All real numbers. You can take anything and multiply it by 16. You can take anything and cube it. So what that means is this graph is going to go to the left and the right forever. It doesn't look like it's going fast, but it is still going to the right very slowly and to the left. And how about the range? What kind of answers do we get for the range here? Yep, Leo? We also get all real numbers. Okay? Because the graph is going to go up forever, it's going to go down forever, and it's connected. Okay, we're going to learn polynomials are always connected functions, meaning you never have to pick your pencil up to draw it. Okay? So the range is also all real numbers. In fact, the domain, that's a characteristic of any polynomial. Any polynomial always has that as a domain, but not that as a range. Anybody think of a graph that's a polynomial that doesn't go up forever and down forever? Maybe a little more basic than the one that we just drew? Yeah? A parabola. A parabola is a polynomial. Domain is all reals. But the range, depending on how you sketch it, either has a minimum and goes up, or it has a maximum and goes down forever. Okay? So there's a lot of characteristics we can classify based on an even, or in this case, an odd polynomial. All right, let's look at this one. So this says a rectangular pool has dimensions 30 by 50 feet. There's going to be a sidewalk around the pool, and it's going to be a uniform width x. They tell us that the area of the sidewalk is 600 square feet. What is the width of the sidewalk? So in this problem, what do you think a good approach would be to solving it? Might make it helpful to kind of organize some of this information in a different way. Yeah. Yeah, let's make a sketch. Okay. It's not the only way to solve it, but it's probably, if you're a visual person, that's probably the best way to do it. So we have a rectangular pool, 30 by 50 feet. Not sure why when I scroll it's a little strange. Okay, so let's try making a pool 30 by 50 feet. So that's 30, 50. And we're going to have a sidewalk around the pool of uniform width x. So what I'll do, I'm going to move my numbers actually to make things a little clearer. That's my sidewalk. It's supposed to be uniform width. That'll be 30. That'll be 50. I think that's a little clearer. All right. And what did they tell me the width of the sidewalk was? Yep. X feet. So this is x feet, and that's x feet. Uniform width all the way around. The other thing we do know is the area of the sidewalk, which is 600 square feet. So we're going to have to use that somewhere. So how could I figure out, I want to come up with a formula first. And we can think of it in terms of like, we have that big rectangle and we have that small rectangle inside. How could I come up with a formula for the area of the sidewalk? What would I have to do in that picture to find the area of the sidewalk? And try to think of it as just two rectangles. Thoughts on how you could get the area of the sidewalk? It's going to involve finding a couple areas and then doing something with them. Yeah?
Well, you have to add 2x to 30 and 2x to 50.
Okay, so if I wanted to find the actual length of this big rectangle, we are going to do that. But that's even thinking ahead a little bit. So what could you do with the big rectangle and the small rectangle to just get the area of the sidewalk? And then we'll figure out exactly what do we have to multiply and all that stuff. Yeah? Do you see what you have to do? Subtract. What would you subtract? Yeah, the area. If you take the area of the big rectangle, and we could just call it the area of the pool, because that's really the small rectangle, minus area of pool. What you would be left with is that strip around the edge, which is the sidewalk. So now we just have to calculate all those things, or if something is given to us, we can just plug it in. Let's start with area of the sidewalk. Do we know the area of the sidewalk? Yeah, what is that, Trevor?
600 feet squared.
Yep, so let's fill that in, 600 square feet. Now, we have to figure out the area of the big rectangle. So I'm going to go back to Rebecca, because you were telling me a little bit about how to do that. Let's just start. What's the formula for area of a rectangle? Length times width. So how were you figuring out the length of the big rectangle? What did you do?
You have to add, because there's two sidewalks on the ends, you have to have 2x
So you have a sidewalk there and there, yep.
plus 50.
Plus you've got the section in the middle, which is 50. So the length is 2x plus 50. And the width, we're going to do the same idea. What would the width of the big rectangle be? Yep, Jay?
2x plus 30.
Yep, would be 2x plus 30. Now we're going to subtract the area of the pool, which we can figure out because we know both the length and the width of the pool. What's the area of the pool? Yeah.
No. I'm sorry. I'm thinking of something else. Hold on. Sorry, 1,500.
Yes, 1,500. All right, so now let's do that out and see what happens. So I have to FOIL this. So 2x times 2x gives me 4x squared. What's 2x times 30? And then 2x times 50. So combine them together. 160x. And now you've got, what's 50 times 30? Yeah. So we've got 50 times 30 is 1,500, but then we have minus 1,500. So what happens there? That just cancels out. Okay, so there's our equation. And what kind of equation is that? It's a quadratic. So when you solve a quadratic, usually you try to get it equal to what number? You get it equal to 0. So we're going to move the 600 over. That's 160 minus the 600. And then, does anybody see anything we can do there to make those numbers a little smaller? Just, it doesn't really make a huge difference, but a little bit. Yep. Yeah, we could divide everything by 4. So we get x squared plus 40x minus 150. Now, at this point, we could try to find two numbers that multiply to give us 150, and then add or subtract to give us 40. But I'm not sure if it's going to come out nice. So how else can I solve it if I can't factor that? Yeah? Quadratic formula. And Shauna, what are the three variables in the quadratic formula? So A, B, and C. And can you tell me what A is in this case? 1. Dylan, B?
Dx. I'm not sure.
Okay, you're close.
What dx squared?
No, you were closer before. Yes. Just the 40. So when you plug into the quadratic formula, just the coefficients, just the numbers. And C, negative 150. All right. Now, does anybody remember what the quadratic formula is? Because now we need that. Yes, Megan?
Negative b times square root of
Well, hold on one second. Negative B
plus or minus
yeah.
square root of a squared minus 4ac
divided by 2a. So I did b squared as she said it, 1600 minus 4a c all over 2a. All right, now under the root, I'm subtracting a negative, so that's going to cancel and become a positive. So I've got negative 40 plus or minus the square root of 4 times 1 times 150. It's 4 times 1 times 150. 600 plus 1600. So 2200 divided by 2. All right, and let's see what the square root of 2200 is. I'm guessing it's bigger than 40. Yep, 46. So one of the answers here I really don't need to worry about because we're thinking about width of a sidewalk. Which one don't I have to be concerned with? The negative. So I'm not even going to worry about the negative. It doesn't make sense in the problem. So we're just going to do, that's the square root of 2200. I'm going to subtract 40. So that's the numerator, negative 6.9. And then I'm going to divide by 2. So the width of the sidewalk is about 3.45 feet. And you could always check that by plugging it in and see if you actually get 600 square feet for the area of the sidewalk. But I'm pretty sure we did that right. Okay, any questions on that one? So you might see the same kind of problem in the homework where it says you have a picture and you're going to put a border around the picture, and they tell you the border around the picture is 20 square inches. It's exactly the same kind of problem. It involves a quadratic equation. Okay. So I think the next thing we're going to look at here is projectile motion. So if you've taken physics or you're in physics, is anybody in physics right now? Yeah. You probably haven't done this yet, I'm not sure. But this is the height, this is the formula that models the height of an object after a certain amount of time. And this version assumes that you're working in feet and seconds. If you've done this with a negative 9.8, has anyone seen that number in physics yet? Negative 9.8? That's the acceleration due to gravity, but that's in meters per second. So this is feet per second. That's the negative 16. Okay. Anyone have a guess what T stands for in this formula? Yeah, it's the time. Okay. So T is the time. That's written up above after T seconds. V sub 0 is the initial velocity. So if you were throwing an object in a projectile path like that, V sub 0 would be how fast the object leaves your hand. And S sub 0, that's the initial height. So if you're throwing an object, maybe when you release it from your hand, it's like 5 feet off the ground or something. You could also do the same kind of projectile motion problem, throwing something off the top of a building. And the initial height in that case would be the height of the building. Assuming you're calculating when it hits the ground that the building is on. And again, you have to use units of feet and seconds in this formula. Okay, so any questions on that formula? All right. So you do need that formula if there was a problem on a test about projectile motion. I wouldn't give you that. Okay, so you have to know that. Okay, and you can also, for this test, you can have a reference sheet for the first test. All right, so it says a model rocket is shot straight up from ground level with an initial velocity of 64 feet per second. I want to figure out at what time the rocket will be 50 feet above the ground. Okay, so let's start to fill in our formula and see what happens. Okay, so it starts off S of t equals negative 16 t squared plus v sub 0 t. What's the initial velocity in this problem? Let's scroll up a little bit. Yeah. 64 feet per second. Plus, the last part is the initial height. What's the initial height in this problem? Zero. How do we know that? Round level. Okay, so this time there is no initial height, so you could just put plus 0. And now they want to know when the object is 50 feet off the ground. So where does that get plugged in? Yeah, S of t. So we're going to fill in 50 equals negative 16 t squared plus 64 t. Okay, any questions on just setting up the formula? All right, now one way we could solve this is exactly like we just did the last problem. But I'm going to do this on the calculator. So I'm not going to use quadratic formula to solve this. I have two sides to that equation. I have 50 on the left, and then I have my formula of negative 16t squared on the right. So what I'm going to do is an approach we've done before. I'm going to put a line at 50. If you have anything else, just clear that out first. And then I'm going to put in my graph. Negative 16. And you have to use x, okay, as your variable. So negative 16x squared plus 64x. Now, y max is the height that the object is going to reach. We don't know how high it's going to go. So let's at least set y max maybe to, I don't know, 100 feet. If we need to go higher, we can. What's the lowest that this object is going to go? 0. It's not going to go below ground. In terms of time, x is time. So we don't have to look at negative time. And let's go up to 10 seconds. If it's not in the air that long, then our object, it'll stop, because we're not going to look below 0. So there's 50. And there's the path of our object. Now, why does it cross 50 feet twice? Because it says at what time will the object be 50 feet above the ground? And it looks like there's 2 points where it's exactly 50 feet. But why 2 points? Yep, Caleb?
Once when it passes 50 feet, and once when it's falling back down.
Yeah, so it hits it twice. So what we have to do is calculate each intersect point. Kind of think of this if you were doing quadratic formula. This is your plus or minus answer. These are both your answers. So second, calc, intersect. I'll do the one on the right. If somebody can do the one on the left, that'll save us a little time. So I got a point on the blue curve. I got a point on the red curve. And it is important where you put the guess, because it's going to give me the one I'm closer to. So on the way back down, it's about 2.94 seconds. Okay, so when will the object be 50 feet above the ground? Between something and 2.94 seconds. Does anybody have the Other intersection point? Leo?
1.06.
1.06. So between 1.06 and 2.94 seconds, the object will be 50 feet above the ground. Now, if it said, when would the object be exactly at 50 feet, you would just write the 2 times. But in this case, I put between the 2 times. Part B. What is the maximum height, and when is the maximum height reached? Well, you can see from the line in red, there is a maximum there. And I'm going to show you something else on the calculator. The calculator can find that maximum for us by going second calc, and it's the option right above intercept. It's maximum. Okay, the way this works is, you have to move to the red curve. Start by picking a point that you know is definitely to the left of your maximum. So the calculator puts in a dotted line and says, I'm going to look between that dotted line and put in another dotted line to the right. So the calculator is going to look for a maximum between those 2 dotted lines. Because there is only one maximum between the 2 dotted lines, the guess doesn't really matter. Okay, so there's the answer to our question. We just have to interpret it correctly. All right, so looking at that graph, does anyone think they can tell me the answer to either part here? What is the maximum height, or when is the maximum height reached? How about Abby? Can you tell me, looking at that, we'll start with what the maximum height is?
Well, round up to
2 for the maximum height? Well, in part A, think about what we just said there. When will the object be 50 feet above the ground? So if we just answered the question when the object is 50 feet above the ground,
64.
right, 2 couldn't be the maximum height. So remember, x is your time value. Okay, that's what you plug in for time. Y is your height. Okay, so the max height is 64 feet. And that occurs, and we're going to round it exactly like Abby just said, 2 seconds. Okay, if the calculator gives you an answer that's like 1.999999, it should probably be 2. And we could use calculus to prove that that's exactly the answer and get exactly 2. But the calculator is just giving us an estimate the best that it can, but we should round that to 2. Okay, we're not going to learn how to do that algebraically using calculus in this class. Okay, that's how we will do it. So max height, and this occurs at 2 seconds. So any question on how we did a maximum on the calculator? You can also do the same thing with a minimum. Okay? If you had to find a minimum, it's the option, same menu, and you do it the same way. All right, so I think the last thing in this section is what's called a piecewise defined function. So the big thing here, I want to show you how you type it in on the calculator. So in a piecewise defined function, the way it works is the domain is split into several parts. So basically, you can think of a piecewise function as 2 different functions graphed together at the same time. Okay, 2 different functions graphed at the same time. And there's an example of a piecewise function. So the idea is, depending on the value of the number that I give you, it's going to control which one of these formulas you use. If I give you a value of x that's less than 1, you are going to plug it into this formula to get the result. If I give you a value of x that's greater than or equal to 1, then you're going to plug it into this formula to get the result. Okay? And you can have more pieces as well. In this case, I just split the domain into 2 parts. Okay. And what I want to show you is just how you type this in on the calculator. Does anybody know how to graph a piecewise function on the calculator already? You do? Can you go ahead and tell me how do I do it?
So you, on y1, put in x minus, 3 minus x squared.
Anything special about how I have to put it in?
Oh, in parentheses.
Yes. Yes. Yeah, very good. You have to put it in parentheses. If you forget it, it messes up. So 3 minus x squared. Okay.
And then you do like the division symbol.
This symbol? Division?
Isn't that what we did?
Well, we're on the right track. We've got the function in parentheses, but then next to it you want to put the condition. So the condition is when x is less than 1. So to get to the less than menu, you press second math, and it brings up all your inequalities. That was second math. So it's only going to graph that when x is less than 1. And then it's going to graph something else, x cubed minus 4x, and put the condition in for that. It all has to be in parentheses, exactly like I'm doing. So x, second math, greater than or equal to 1. So I'm going to do zoom 6. Put my window back to the standard window. And let's see what it looks like. So notice all of a sudden it just stopped in blue and then it traced along the x-axis, and it's doing the same thing in red right now. It shouldn't be tracing along the x-axis. It's because the calculator doesn't know what to do, because you said only graph less than 1, and the calculator has to do something. So just ignore those lines. Okay, so you should have gotten a picture that looked just like that. And just pretend that the axis is all in black. Oh, you get the idea. And the other thing is, what kind of symbol should be on the end of the blue one? Open circle or closed circle? Yep. Open, because we're not including 1 as part of the blue graph. We are including 1 as part of the red graph. So if you want to be very technical about it, that's how the graph should look. And so again, piecewise function, it's just 2 or more graphs kind of sandwiched together. Sometimes they connect, sometimes they don't. In this case, they don't connect. And that's fine. Okay, so any questions on graphing a piecewise function? All right, so that's most of, I think, the new stuff for today. The last thing we're going to look at is section 1.4, which talks about slope. Y equals mx plus b, slope. So I'm going to go through that very, very quickly, even though it's Algebra 1, just to make sure people remember that stuff. If you already know slope and y equals mx plus b, you don't have to take down the formulas, but I will be testing you on it. So as long as you know it, you're all set. All right, so y equals mx plus b, that's the form of a line we use most often. The coefficient of x, that's your slope, and b is your y-intercept. What does that mean, y-intercept? Leo?
When the line intersects the y-axis.
Yeah, it's where the line crosses the y-axis. Okay, so very basic stuff. Anything that can be written in that form, we call a linear function. So y equals 2x plus 6. That's a linear function. Okay, because it's written in that form. There's no restriction on b. Okay, b can be any real number that you want. That's what this says. B is an element of the real numbers. M also has to be a real number, but there is one restriction on m. M can't be 0, because if m is 0, then this part of the equation disappears, and you just get y equals a number, like y equals 5. That's not the definition of a linear function. That's called a constant function. Okay, so if you just have y equals number, that's a constant function. It's still a line. Constant function, the picture of it is a line, but it doesn't fit the definition in our book of a linear function. Okay, any questions on that? Okay. So let's look at an example and see if we can find an equation. It says a house was purchased 10 years ago for $60,000. 10 years, $60,000. And then it says this year, the house is worth $85,000. Assuming there's a linear relationship between the value of the house and time, which may or may not be true, but in this case it's true, find an equation to model the situation. And then we'll have to figure out when the house was worth a specific value. Well, using this information, we can almost create coordinates. When was the house worth $60,000? Yeah? Yeah, the first year. So why don't we think of that as like before any time went by? At the beginning, the house was worth $60,000. And then when was the house worth $80,000? Yeah. Year 10. So it's basically like we have a set of coordinates. And what we want to do, kind of takes me right into the next slide, so let me put that up at the same time, is to find the slope. Okay, so the slope is change in y over change in x. What do I get when I do change in y here? What's the change in y? 20,000. What's the change in x? Right, so the house went up $20,000 in 10 years, or basically the change per year is what the slope is. So what's the change per year? 2,000. That's my slope. Now, the other thing I need is the y-intercept. Am I given the y-intercept somewhere in those, well, I won't circle it because that's not the answer, but somewhere in those coordinates? Is there the y-intercept, Jan?
It's 60,000.
Yeah, the y-intercept is 60,000. So now you could write your equation. Y equals mx plus b. And that's the answer. So find an equation to model the situation. Yep, we did that. Now if they want to know when the house was worth $71,250, where would you fill in $71,250? Yep, Megan? You'd fill it in for y. Okay, I'm not going to go through and solve it, but you would have 71,250 plus 2,000x plus 60,000, and solve from there. Okay, Okay, and if you want to know the answer, I think it comes out to 4.5 years. If you go ahead and solve it, it's after about 4.5 years the house was worth that much money. Okay, so you should know how to set up a basic linear equation. You should know how to find the slope, and you should know the two special cases. Okay. If your change in y values is 0, okay, if the numerator is 0, that's a horizontal line. Okay, that has a slope of 0. If the change in your x values is 0, that's like you're trying to divide by 0. You can't do that. That's an undefined slope, and that's a vertical line. Okay, so on a test, if you calculate a slope, and let's say you leave the answer like this, I would only give you half credit for that, because I don't know if you know which of the two cases that is. Is that 0 or is that undefined? Which one is that? That's 0. Same thing if you left an answer like this, I'd give you half credit, but you got to tell me that that is undefined to get full credit. Okay, so those are your two special cases. Okay. Two special cases of equations of lines that aren't in the form y equals mx plus b, but they still are equations of lines. They're just not linear functions according to our definition, are y equals a number and x equals a number. So if you want to put a horizontal line going through a certain number, you set y equals, put the number. If you want a vertical line, you put x equals. So what would be the horizontal line that goes through the point 2, 3? About Tanya? Can you say the whole thing? Y equals 3. That's the horizontal line that would go through the point 2, 3. How about the equation of the vertical line that goes through 2, 3? About Sean?
X equals 2.
Yeah, x equals 2. And if you graph those, the vertical and the horizontal line, they would cross exactly at the point 2, 3. All right, how would you take something like this and get y by itself? What would be your first step? Okay? Subtract the 2x. And would you write it as 6 minus 2x or negative 2x plus 6? Yep, I like that idea. And your last step would be to divide everything by 3. Why would you do that? What's the point of taking something that was written like it is on the top and rewriting it on the bottom? Well, Sam?
So you can graph it easily.
Yeah, so you can graph it easier. Now you can see the slope and you can see the y-intercept directly. Okay, so that's an important skill to have. Okay, another form of the equation of a line we don't use as much is point-slope form. Sometimes we use it. It's good if you're given an example like I have on the board. Okay. If you're given a point and a slope, you can use that to get the equation of a line if you want. So you do something like y minus 3 equals m times x minus 2. And now you could do the same trick that I just showed you in the last problem. You could distribute out the 1/2 and then add the 3, and you could write the answer to this in y equals mx plus b if they asked for it. Or technically the directions in this case just say find an equation. Well, technically we've done that. It's not in y equals mx plus b, but we did find an equation. Again, I'm going kind of quick through it because it's really Algebra 1 stuff. There's one other form of the equation of a line that we generally don't use this one very much, but it's when you get it equal to 0. We do that a lot with quadratics. We get them equal to 0. Okay? But I'm just showing it to you in case you see general form. It puts everything on one side and 0 on the other. Okay, I'm not even going to go through an example of it. Parallel lines. How do the slopes of parallel lines compare? They're the same. Yep. So they have to have the same slope, but they have to have different y-intercepts. If they had the same slope and same intercept, they wouldn't be parallel. What would they be in that case? They'd be the same line. Yeah. How about perpendicular lines? Does anybody remember what their slopes have to be perpendicular? And there's two parts. Caleb?
Opposite reciprocals.
Yep. The slopes have to be opposite reciprocals. So again, I'm not going to go through this problem, but the kind of problem you might see is write an equation of a line that's parallel to this one and passes through that point. So the first step would be to take what I just circled and rearrange it for the slope. Find the slope. And then once you have the slope of that line, you want to find something parallel to it. So you're going to use the same slope. I would plug that in for m, plug 1 in for x, and plug -2 in for y. And you could use your point slope form, just like I did here. Just fill in those three numbers after you get the slope. And the last thing, which I think there's only one problem in the homework, is graphing an inequality. So something like this. And you have to decide where to shade. So, same as graphing a line. You don't graph it any differently. The only thing you have to do is if you have a less than or equal to, a greater than or equal to, you use a solid line. If it's a less than or greater than, you use a dash. Shade below for those two symbols. Shade above for those two symbols. Okay. And that's graphing a linear inequality. Okay. And I'm not going to go through that example right now. I would probably rearrange that in y equals mx plus b first. Okay. So that's the homework for tonight. If you want to copy it now, you can. If you want to just get it, it'll be on YouTube in about 5 minutes. So it's 32 to 37, 45, 46, 50 to 52, and 55 to 57. And then page 42 just kind of skips around a lot. 2, 7, 8, 11, 16. 17, 20, 24, 27, 32, 44, and 77.